They can watch it later. All right, let's take a look. I want to do a quick edit here, and I apologize for you guys because this is actually the bigger of the classes, but I just can't seem to line up a lab day for you guys. Um, and I know that after the MYP projects on Thursday, I'm not going to feel up to much on Friday. So what we're going to do is we're going to switch that to a lab day. We'll do the laboratory I talked about. Basically, what we'll do is we'll make our own indicator solution. And you guys know indicators from before. We're going to make our own indicator solution out of cabbage. You love cabbage? Yeah? How do you like it? Like stuffed cabbage rolls? Yeah, a little bit of bacon. This is what we use is red cabbage. But if you look in the store at red cabbage, what color is it? Purple. Well, why do they call it red cabbage if it's purple? What'd you say? Hey, what? No, it actually starts purple. It's actually just the opposite. But when it comes to the plate, it's usually cooked with some apple cider vinegar or something like that. And the apple cider vinegar actually is an acid. So whenever people see it, they actually see it plated when it's red. So it starts purple through the cooking process. By adding that acid to it, it turns red. Now, the cool thing about red cabbage is that if it interacts with a base, it actually turns green or blue. So this can actually be used as what we would call a universal indicator. And this is just a compound in the cabbage itself that gives it that color. That once it hits a certain switch on the pH, it exhibits a different color. It exhibits a different color. All right. So that's going to finish the week for us. You guys don't have MYP personal project, but tomorrow is shorter. I don't know even if we're going to get through this today to get onto a discussion of buffers tomorrow. Those of you at home that will be doing this lab, I will try to get that laboratory up there by the end of the day so that you can read it. It is pretty simple, but it's kind of interesting and fun. Take a look then at the work that you guys did last night. I believe we had this problem. So if we have delta G equals delta H minus T delta S, you would define the T. So we need to rearrange the equation. So how would you guys do that? Delta H plus delta G equals T delta S. We have the delta S and we have the delta H and the G. Since it's plus 0, we can get rid of that. We have the delta H, so that's 30. Take that 30 divided by 90.4. And we get 0.33185. For that. That can't be right. That's a made up problem. I wonder if the delta S and delta do that. But yeah, that that can't be the boiling point. Bromine, it's got to be much higher than that. But that's the working of that equation, right? Delta G equals delta H minus T delta S. So, thank you. There we go. That's my man right there. Yeah, it's early. Watch me for those mistakes. Good call by him. What we have here is we have to change this 90.4 joules to kilojoules, or change this from kilojoules to joules. So if we take that delta H, and I'll go ahead and do this one to the joules. We're going to divide that by then the 90.4 joules per mole, and that's per mole Kelvin. So we have basically per mole here and per mole here, but then we have 1 over K, which is going to give us the Kelvin. The joules will cancel out, and we get 30,000 divided by 90.4. That makes more sense. 332 Kelvin. Still seems kind of low, but 332 Kelvin. So at 25 degrees Celsius, equilibrium constant for this is 0.281. So again, the R we need to use for this is that 8.314 joules per mole Kelvin. And that's actually given to you on in the appendix. So there's our R. We're going to put a negative in front of this whole thing. It's at 25 degrees Celsius, so we need to add 273 to get that to Kelvin. And then we have our natural log of K, which is 0.281. We are going to put this into there, and we're going to get the Kelvin to cancel out there. So we're going to end up with joules per mole. We get negative 3,145 joules per mole. They may ask you to have that in kilojoules, which would be negative 3.145. Probably around that. Kilojoules per mole. And again, since this is negative, delta G being negative means that this reaction would be favoring the forward direction. Excuse me. Don't forget to sit here and take a few minutes to look at this equation, and then make sure you can go back and forth and determine how delta G can be either negative or positive with changes in temperature. All right, we were also asked this one. It looks like delta G equals delta H minus T delta S. It says for this system, sulfur dioxide plus oxygen yielding sulfur trioxide. Delta H is negative, so that means it is exothermic. So we're going to have heat on the product side. Is that favorable for a reaction? If delta H is negative, is there a better possibility for delta G to be negative? Yeah, right? Because if we have a negative minus something, unless this is a negative, then that has a better chance for delta G to be negative. So that favors that forward reaction. Well, let's look at delta S real quick using our ideas. Delta S, is it becoming more or less random? So it's entropy going to be going up or down. But all of these are gases. So what's our best case scenario? What do we base it on? Probably the number of moles. So on this side, we have 2 + 1 moles. And on this side, we're going to 2 moles. So that is actually going down. That means it's becoming more organized. So that means that delta S is probably negative as well. Is that beneficial for a reaction going forward or no? We have a negative heat, but we have a negative delta S. So if we subtract a negative, what is that? Positive, right? Subtracting a negative would actually be positive. So if that is bigger than our delta H, that means we're not going to favor that forward reaction. Because then delta G will be positive, which favors the reverse reaction. We good on that at home because I'm getting some stares here and I'm not sure. With these masks, I can't tell the overall. They're already asleep. All right, so remember, if delta G is negative, then that favors the forward reaction. If delta H is negative, that's a good chance for delta G to be negative. The problem here is that we are becoming more organized. So, like we said, the universe does not tend to get more organized. You look at the stars, right? I've got to put energy into that to reorganize it. Otherwise, it just gets like that. So, assume that one has an equilibrium mixture of these substances. Predict the effect of each of the following changes on the value of the equilibrium constant and on the number of moles of SO3 present in the mixture at equilibrium. Briefly account for each of your predictions. Assume that in each case, all other factors remain constant. So if we decrease the volume, that's going to put the squeeze on that. How does the system alleviate a decrease in volume? Or if we decrease the volume, that increases the pressure. We know that every 1 mole of any gas takes up 22.4 liters at S2P, right? So if we don't have as much room, what is the system going to do? It's going to favor the side with the least moles, right? Just like if you're out on the dance floor and you're listening to a live band and a bunch of people get around, you take up less space. But if the crowd disperses, like a big group leaves that's right around you, so then you can pick up as much space as you want. Same thing with this system here. This side is the least number of moles. So if we decrease the volume, SO3, concentration of SO3 will increase. Briefly account for each of your predictions. With a decrease in volume will increase because decrease in volume will favor the reaction with the least number of moles. Which is the forward reaction. Right? So we get more moles of SO3 forming because of less space. All right. Adding oxygen to the equilibrium mixture. Is oxygen in the reaction? Yes. So if we add oxygen to the mixture, oxygen is a reactant. So if we increase the concentration of the reactant, what does that do? Does it favor the forward or reverse? Favors the forward because adding more reactant will favor the forward reaction. Therefore, you guys know therefore from, yeah, you guys put geometry, right? Therefore, concentration of SO3 will increase. It says number of moles. So maybe we should actually put that instead of concentration, number of moles of SO3 will increase. That way, if somebody is grading it and he's throwing concentration, that way change it up. Since it does say the number of moles up here, we know that if we increase the number of moles without changing the volume, it's just like, I would probably put number of moles in there instead of concentration if I would have. Raising the temperature. Well, we know that this is exothermic. So what is raising the temperature going to do? What's that? Favors the reverse, right? So in an exothermic reaction, increasing the temperature favors the reverse reaction. Therefore, moles of SO3 will do what? Decrease. Boom, boom, boom. You could put concentration, but again, it actually says what happens to the number of moles. We increase. All right. Oh. For each of these, K sub BQ will remain constant as well. It does say predict each of the following: changing pressure and changing the amount of concentrations of these guys. It's not going to change that. But if we change the temperature, if we take a look up here, if that temperature is higher, what does that do to our delta G? Makes it lower, right? So if we look at our formula here, if delta G is lower, what's going to happen to our K? Right? I think so. We have to look at that. If we increase temperature in an exothermic reaction, I believe that would definitely make that lower. I'll check into that. Make sure. But I did not see that that's for the effect of the equilibrium constant. So just reading it that second time. But definitely these two, not going to change the equilibrium constant. The only thing I can think of that would change the equilibrium constant in this case, dealing with the Chatelain's principle, would be a change in temperature. All right. Let's do one more, and then we'll give you 2007 part A for homework. This is one thing that we haven't dealt with very much, and that's using pressures with K. Key things with this is that whenever you do your case of EQ, and I know that this seems silly to me too, but instead of using brackets, because brackets in chemistry actually show concentration, when you use the pressures, you should use, what are these? Yeah, you should use those instead whenever you're dealing with the pressures. The other thing is that everything taken into account, it's basically the same exact setup. So if we take a look, ammonium hydrogen sulfide is a crystalline solid that decomposes as follows. Here's our ammonium hydrogen sulfide. It makes ammonia and H2S, hydrosulfuric acid. So some solid ammonium hydrogen sulfide is placed in an evacuated vessel at 25 degrees Celsius. Now with gas law problems and equilibrium, one of the things that you're going to have to realize is you're probably going to have to end up using the ideal gas law at some point. So it's good to mark that temperature. The reason why you'd have to use the ideal gas law is because with pressure, ideal gas law allows you to get to moles, right? After equilibrium is attained, the total pressure inside the vessel is found to be 0.659 atmosphere. So this might actually, this does actually use Dalton's laws of partial pressure. So if you recall Dalton's laws of partial pressure, the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2, so on and so forth. Some solid NH4HS remains in the vessel at equilibrium. Do we care about solids that much at equilibrium? No. For this decomposition, write the expression for Kp and calculate its numerical value at 25 degrees Celsius. So if we take a look with an ice table, and man, did I not leave enough room here? Actually, maybe I can do it here. ICE. So we don't care about this one, but we have 0 of this and 0 of this. So that's going to be a plus X and a plus X, which is going to make these two add up. And it's 1X and 1X. So we need to find if we have the total pressure is 0.659 atmosphere, right? We have basically 0.659 atmosphere. Each of these are going to have the same pressure because we're making the same amount of each of these. And let's just take it at STP, even though it's not. 1 mole of any gas, right, takes up the same amount of space, so it would have the same amount of pressure. All of those things being considered, that means that this total pressure is equal to X plus X, which is 2X. 0.659 divided by 2 equals 0.330. The pressure of each of these gases is equal to 0.330. Well, with K sub EQ, or what, this is a more specialized thing, so this is Kp. Remember, we don't care about the solid, so that's going to be 1. But we have 0.30, 0.330. Multiply these together, and I'm just going to keep that times 0.329. We get 0.1085, or Kp equaling 0.109. Is it too loud back there for you? No, it's too loud for me. These Ks, remember, we don't bother that much with the units on this, But if they did ask you for it, it would be atmosphere times atmosphere, so atmosphere squared. I've only seen a few times where they ask for units on K over the tests. Some extra NH3 gas is injected into the vessel containing the sample described in Part A. When equilibrium is reestablished at 25 degrees Celsius, the partial pressure of NH3 in the vessel is twice the partial pressure of H2S. Calculate the numerical value of the partial pressure of NH3 and the partial pressure of H2S in the vessel after the NH3 has been added and the equilibrium has been established. So what they're telling us here is, again, that temperature has not changed. So that means whatever the Kp here, that's also the Kp here. This time some extra NH3 gas is injected, and it says that the partial pressure of the NH3 is twice that of the H2S. So if this is the NH3, that will be 2x, and the H2S will be x, and the Kp we have from up here is 0.109. So we have 2x times x is equal to 2x squared. So divide both sides by 2 and then take the square root. .233, what do they want? They want the partial pressure of NH3 and H2S. So this is x. So H2S's partial pressure will be 0.233 atmosphere. And the partial pressure of the NH3 will be that times 2. 0.467. You are more than welcome to shut that door if you want. What are they even talking about? In a different experiment, NH3 gas and H2S gas are introduced into an empty 1-liter vessel. Again, at 25 degrees Celsius, the initial partial pressure of each gas is 0.5 atmospheres. Calculate the number of moles of solid NH4HS that is present when equilibrium is established. So again, if we take a look here, we have each gas is 0.500. So we need our balanced equation. NH4 HS yields NH3 plus H2S. So we have, and this is exactly like with the concentrations, we can use the partial pressures in a nice table. So how much of this do we have at the beginning? So many words, right? You can't see it. What's the key word that tells us how much of this we have at the beginning? Players from home? This right here. Right? It's empty. So that tells us how much solid do we have at the bottom of an empty thing? We have 0 of that. And it says that we have 0.5 atmospheres of each of the gases. So the initial pressure of each gas is this. Calculate the number of moles of solid. If there is no solid present, we know that this is a reversible reaction. Some solid will deposit on there. We got to find out how much that is. But in reality, it's not a pressure, so we can't actually like call that X, right? So we have to actually backwards engineer this one. It's kind of an interesting one. Because these are pressures, that does not attribute to moles. So we'll have to find this some other way. We'll have to find the amount of that some other way. 0.500 minus X. 0.500 minus X. So if we take a look, we do know that it's still 25 degrees. So we've got the 0.109 squared. So if we take the square root of that, we get 0.330. And then what? If we got 0.500 minus X, we go ahead and we have X over here, and we subtract that 0.330 from it. So we get 0.5 minus the 0.330. That gives us 1.70, 0.170. Atmosphere. So that's the X. So that's how much we've lost of each of these gases, right? So by knowing that pressure, this problem gets crazy. By knowing that pressure and PV equals nRT, you with me? By knowing the pressure that we lost here, whatever that is, we can find the moles that was used up. And for every 1 mole of this gas that's used up, how much of this do we get? 1 mole. Yay, raw fun, right? So we have the pressure of the gas is this. We have the volume of the container is 1. We want to find the moles here. So I'm just going to rearrange this PV over RT equals N, where the pressure is 0.1, can't read. Yeah, right. It's because I have that right there. Why do I have that right there? I should say X. I think I was going to rewrite this. So if we take a look, let's try this again. 1.70 atmospheres for the pressure. The volume is 1 liter. The R constant here is going to be, since that's atmospheres, are 0.0821 atmosphere liter per mole Kelvin. And our temperature here is 25, but we need to change it to Kelvin, which is 298. You think I'd have that one memorized by now? Our kelvins cancel out, our atmospheres and liters cancel out. We have 1 over mole, which is going to give us mole. So 1.7 times 1 divided by 0.0821 divided by 298 gives us 0.0695 of the ammonium hydrogen sulfide. What does it want? Oh, look at that. Sweet. Cool. Questions there? Let's read. Yeah.
Mr. Jackson.
Yeah.
So how did you set up that equation when you have the radical 0.109 equals 0.5 minus X? Where did those numbers come from?
Okay. So during this reaction, if we take a look, both of these gases start with an initial pressure of 0.50 atmosphere. We don't have any of the solid. So since this is an equilibrium, we have to make some of the solid. Since this is a 1-to-1 mole ratio, whatever we lose of this, we lose of that to make the solid. So at equilibrium, then the atmosphere, like we can put pressures in an ice table just like we can concentrations. So we have a 0.500 minus whatever that pressure is that we lost for each of these. So going back to this, since we're at 25 degrees and it's the same equilibrium expression, we don't need the 2x here because it's just this and this. So that becomes this times this, which is the same as this squared.
Oh, I see. Okay.
Yep. And since this is 0.109, that's the Kp, I took the square root of both sides. And keep in mind, again, this is probably the hardest part in my mind of this problem. Maybe you guys may be like, yeah, that's the easy thing. Is you can't just solve for the x like we would be used to for molarity, and then divide and then multiply by the volume to get the moles for this, because these are pressures and this is a solid. That's why we have to use this PV equals nRT. We take one of these, it doesn't matter which one because it's all the same, and we calculate the moles that was used up from X, and then that's going to be for every this many moles of this and this many moles of this that react, we'll make that many moles of that, right? And that's what we got. With the pressures, the only thing is keep in mind, you're probably going to have to use maybe a PV equals nRT for some reason. They like this because if we have a 1-to-1, then it's going to be x plus x, or if it were a 1-to-2, then it would be 1 plus x plus 2x type of thing. So they can actually, you can actually solve for pressures by knowing the total pressure of the system. By knowing these ratios, and if there was 0 of that at the beginning, you should be able to do that math pretty easily. But don't forget, the equilibrium multiple choice test is online, and you have till Thursday to do it. If you did it Monday, you're fine. As I told you on Friday, I wasn't putting anything that we're covering this week on there. But if you wanted to wait, you were more than welcome to, because I know you guys do have a half day. Please try to get that in. If you haven't gotten 2 tests done yet, if I think there's only one person that has not done any tests yet, so these next 2 you basically have forced yourself to take, so keep that in mind as well. For tomorrow, I'd like for you to try 2007 Part A. That allows you to do the Gibbs free energy, deals with entropy again, as well as delta H. That's all I got. Have a great day, guys. And as I told you, who is it, Lelia and Woodrow? I'll try to get that lab up there today so you can take a look at it. Bye. Obviously, if you have questions, you can always ask.
Sorry, which one did